is world's thinnest prescription eyeglass lenses made instantly in the shop. I will focus on the business part, and some of my colleagues, they will tell more about the market, about the technology, and the way we are making these lenses. So this is the program. First, me on the business part, the strategy that has been behind this development project that has now been running for several years. Then Henrik, my co-founder of the company, he will tell more about the market. Anders, who's also a co-founder of our company, will tell about the technology. And then last but not least, Nikos will tell about the nano imprint and so on, what they have been doing in Greece. The partners in the project, we are 5. DTU, who is responsible, or you can see heading the project. Then we have Nanotypos, a Greek company. We have Optilex in Sweden, who is a producer of traditional lenses today. And then we have PB Management, that is Henrik, and we have B8H Power Consultants, which is me. So we have been running this project together for the last 2.5 years. We have founded a company called ABH Optics for Anders, Bo, and Henrik, so not more complicated than that. And we've been working on this for quite a while. It started all before I joined the project. It started in 2015, where Anders had Chromavision. Then in 2017, Anders and I, we met, and we looked at the potential, the business potential of the technology that they had been developing at DTU. And we looked at different options, optical components, lenses, filters, and so on, but decided that the eyeglass market was what we thought would be most attractive. In that period, while we were looking at these eyeglasses, I accidentally met Henrik, and he claimed that he knew something about this. And so I said we had a cup of coffee, and we discussed the situation, and we decided that it would be good if Henrik could join the team. And I think that's part of the success we've had so far, is that we really have somebody on board who understands the business side of optical lenses, or eyeglass lenses. So in 2020, we got funding from the EU for this project, the Odyssey, that I'm going to tell you about now. And last summer, we founded the spin-out company, ABH Optics, and that we are now ready to go out and get new funding to continue the process. A business needs to solve a problem, and the problem we are solving is an old problem. It's if you need strong lenses for your glasses, then they become quite heavy, maybe 10 millimeters or in that range. And of course, that makes them heavy. It doesn't look very nice. It gives you nose marks. It's not comfortable. With our solution, the lenses will be only 1 millimeter thick, so it means they'll be light. They will give you a better transparent look. You can select any frame you want because there's no limitations due to the thickness of the glasses and so on. So it's and we can do that at the same price as lenses are made today. On top of that, because the way we make the lenses using a laser, we're actually able to make them in the optician shop. So you only have to go to the optician once, because we make them while you're waiting, having a cup of coffee. So that's the vision, that's the idea. The difference between the way traditional lenses are made and the way we make lenses is that instead of having the optical effect in the lens itself, in the lens base, we have replaced one of the coatings on the surface with a meta surface that we can modify with a laser. And this way, the optical effect is just taking place in a layer that's less than a micrometer in thickness, which means that the thickness of the lens is actually determined by the mechanical properties rather than the optical properties, which of course is a good thing. The team behind this is Anders, who has developed the technology that he will tell you about. Henrik, who knows, I would say, everything about the optical space, and myself, who has been in a startup, high-tech startup. So we believe us together, we have all what it takes to make this company a success. Over the years, we have received funding. Altogether today, we have received 2.3 million euros in funding, most of it coming from the EU, but also, as Mikael mentioned, some of it coming from Innovationsfonden and some from the DTU POC grants. But now we are ready to go on and go out and get some commercial funding for the next phase of the project. The market we are addressing is a huge market. The prescription lenses is a 42 billion euro market, and so it's really attractive, and there's good margins in this market. It's also, you can see, there's some large players out there, Essilor, Zeiss, and Hoya. Some of the names you might know, some you don't, because they are not, you can say, the brand names, but they have, you can say, are dominating this market. But there's still a lot of smaller players. Anyway, we don't think that it's the right thing for us to join up with some of the big companies. We think that they're not interested in disrupting their own business, so we find it more attractive to do the disrupting ourselves, or at least start the disrupting ourselves and prove that our technology will work. So therefore, we have decided that we'll do it ourselves. The value chain will change. This is how we are disrupting the business today. Lenses are made in a very old-fashioned, traditional way with a lot of polishing and grinding. We will do away with most of that. What we need is just a very basic lens, of course, smooth on both surfaces, and then we will use nano-imprint, coatings, laser printing to make the lenses, and then they will be cut to fit the frames in the optician shop. Today we have established a supply chain where Optilex is the Swedish partner in our current project, who has a lens manufacturing facility in Sweden where he can make 40,000 lenses per month, so that would be enough for a good start. And then we have Nanotypers, who is you will hear from later, that will do the nano imprint stamps. BenQ is an ALD supplier, so we can make ALD or atomic layer deposition on our lenses. And then we have ABS Optics that will be selling the lenses to opticians together with the laser printers they would need in order to make the lenses on site if they want to do that. If they don't want to do that themselves, we will do it. Our strategy to enter the market is to go for the high power lens segment in the beginning, because that's where the users will have the largest benefit. And later we will expand to all market segments, because there's no reason why not to. And it will be more convenient for the users that they can get the lenses in just one visit to the shop. The niche where we will enter the market is not that small. It's 5.5 billion, and it makes up about 30% of the lens market. All the diopters above 4 is where we will address the market. Already today, the market is split in this way that the main market is addressed by the big players. That means everything between plus and minus 4. And if you have above 4, you can say it's smaller manufacturers of lenses that is serving that market. And this is the market that we will enter, and where we believe that we will have a good case and a good opportunity to enter, because this is where you have the largest benefit from using thin lenses. Long term, we think that we have a good case for entering the main market as well, because of this laser technology that allows us to have the lenses made in the shop. Since we want to have the opticians sell our lenses, of course, there need to be something in it for them as well. And we had made a market survey, and about 50% of the users indicated that they would be willing to pay up to 20% more for their lenses if they could have these super thin lenses. And also 80% of them indicated that even though people usually usually go back to the same optician every time they renew their glasses, 80% said, okay, if they could not get the glasses they wanted at their optician, then they would change to a new optician. So it means that opticians that take our glasses in will be able to attract more business. So that's what's in it for them. Where we are right now is, you can say, at the end of the Odyssey project. We are seeking new funding, seed funding, and then we need to do some more product development before we have a minimum viable product. So part of the funding will go for that. Once we have a minimum viable product, we will go to the market and in a very small scale, in a limited test where we control the environment ourselves, so we are sure that before we expose ourselves to the commercial market, that we have solved all the issues that usually is associated with introducing a new product. So hopefully in 26 we should be able to start selling to opticians. Of course, we'll start in Denmark because that's easy. But then soon after that, we will try to enter the global market. And of course, in that phase, we will need more funding again to be able to expand quick enough. But it's a very exciting area we are in, a very exciting market. So we think that if we get 2.4 million euros in pre-seed funding, we should be able to get to cash positive. And we will use that for salaries, of course, the test centers, inventory, product development, and so on. But by 2026, we should be able to be cash positive and then start the expansion. And of course, the expansion will depend on how the market receives the product, but also on the funding we have available in order to penetrate the market. So that's all for me. Any questions? I think you can also ask questions for now, or you can do it later when you. Yeah, Jan?
When will it be possible to buy, let's say, the first minimum viable product?
That will be in 25 in the test center. What our plan is to simply, together with our other facilities, to set up an optical shop where people can come in, they can bring their own frames, or they can come with their old frames, and then we will fit glasses to fit their frames. This way we can test it in a small way without having to have a big selection of frames and people. So just to keep it very simple and say, okay, but bring your frames and we will give you, and we will sell you the lenses. So that's it.
What about test persons and so on? Is that
That would be part of the product development, where we will look for test persons to validate the product.
The existing players in the market, how do you think they will react to being disrupted if you succeed?
Okay, maybe Henrik should answer that question. He knows them well.
Yeah, I think they will not like it because they have a traditional setup, and this traditional setup they will protect it. And this is actually the part of our strategy is to go direct to the market and show that this actually brings value for the end user. We could also go into the industry with this technology and try to let's say cooperate with the existing players, but they would not like this product at the certain stage because they have invested so much in this traditional setup that they have. So this is part of our strategy, that we go directly to the end consumer and build a value chain. And of course it takes more time, it's more costly to do it in that way, but at the end we will prove that this product is benefiting the end wearer, and it has a value, and it has, let's say, a reason to be in the market. Yes? Price point will be at the same price point in the long term. In the beginning, the price point will be a little bit higher, but you will also gain some benefits from this new product as you do not have it in the old product. Yes?
How many opticians, how many places it's called opticians, or
Yeah.
how many shops are there selling glasses in Denmark?
Around 750 shops in Denmark. And you have the buying groups, and you have the chains, and you have the independent opticians. This is more or less the market. And we have made a study, a survey, trying to figure out where the customers of this future product today are purchasing the lenses. And we are also in that study asking them where in the future they would like to purchase this product. So we have a quite good idea of how we go to market with this new product.
Can I follow up?
Yes?
So I guess, are you going to be the biggest company in the world selling lasers? You're a laser company, right? I mean,
Yes.
Selling, so if 750 shops cover 5 million people, if you want to call them the best in the world, how many lasers are you going to sell?
Yeah.
Yeah, that would be a lot.
Yes.
So I guess you'll be the biggest laser company in the world.
Yeah, or provider. Yeah. So we could see ourselves as a software company actually, and a laser company, rather than an optical company. Yeah, that's a yeah. Sorry.
I assume when you come with some disruption, either you move very fast, or I assume that you have protected IP in order to protect your idea while you are doing probably fast compared to your size, fast transition into the market. But as soon as they realize we will be disrupted, of course, they will do whatever they can to to circumvent whatever protection you have.
Yes.
How do you see that game?
Yeah. DTU is owning the IP. DTU is owning the IP. We have a term sheet with DTU regarding the license, exclusive license to the IP. And in the Odyssey project, we have developed further IP that has not been filed yet. So that's one of the reasons that Anders will not answer all the questions or explain everything. So, but yes, we have thought about the IP, and we have one of the patents have already been granted, and the other one has been applied, and they are very nice and broad patents. So I think
they are covering the invention.
Yeah, yes, yeah. As far as we can tell. If there's no more questions at this stage, then I will give the word to Henrik.
Yeah.
Just
so now we have 15 minutes each, and I will try to do my part in 6 or 7 minutes. So we have questions and you just raise your hand if there's something you want to ask me immediately. So we do it that way.
We can skip that one just to. Oh. So this is just my background. I'm an optician educated. I specialized in contact lenses. I worked with the contact lenses in '85. And at that time, I disrupted the contact lens business by developing a concept to exchange the lenses every month. At that time, you had the lenses for 12 or 18 months. And that brought me into the industry. So I worked for Ciba Geigy, Ciba Vision. And then I studied a BA. And I actually worked many years for the industry, had small jobs as a CEO in Synoptic for a few years, and then I went back into the industry. And for the last 12 years, I worked for Essilor, which is the largest manufacturer of lenses. Essilor is the Coca-Cola of lenses. They have 40% of the market in the industry. They're developing everything, the coatings, the designs, everything that has a value. Essilor has a patent on that. This is why we have been a little bit under the radar with this project, because I don't want them to interfere into our building of this company, and now we have to face that we need to express it more in the public, what we're doing. Today I have, since 5 years, 5 optical shops. I know pretty much about the optical industry, and I have a network in Europe and worldwide, so we know exactly who we can go to if we need something or somebody to help us. The market is enormous. So the total optical market is 100 billion market. The breakdown in lenses Bo showed you is 40%. The 2 large players in the market is Essilor and Luxottica. They merged 2 years ago, and the merge is now finalized. So they are absolutely the large animal in this business. They are owning the lenses, they're owning the frames, and they're also invested in Grand Vision. So now they also own the retail. So they have the whole value chain. And this even more proves that we need to build our own value chain to get this product proved by the end consumer, to bring it into the market, because it's a heavy competitor and we will not be able to compete against Essilor with our product. Then we have Zeiss and Hoyer. Zeiss you probably know as a brand, and Hoyer is a Japanese company. They are quite large in many sorts of products, so only a small fraction of this huge company Hoyer is lenses, and they are the third largest player in the market. The good news is that we will become more and more myopic. So if you think the market is stagnating or people are going to get surgery, yes, maybe they're getting surgery, but they will be more and more myopics. And the reason for that is that we all have these smart devices, and with these smart devices, we keep them actually too close to our head, and the children are doing that. And when you do that, it stimulates the eye to grow. And when you stimulate the eye to grow, you become myopic. So please, don't tell your kids to keep the smart devices here, because that will ruin my future business. Just let them do it. I have tried to tell my kids for many years that they should take it more, keep it a little bit far away from the head, but they're not listening. So we will have half of the population will become myopic. So there's enough business for us. And if you see the Asian market, there are many myopics, because they actually for many years have been reading quite closer than in the European market. And they tend also to have a higher myopic. So for us, where we have a +4 or -4, which is our target market, this is good news. So we just finalized a survey. That survey, we actually wanted to ask the future users of the lenses, which are myopics and hyperopes that have +4 or more, or -4 or more. How are they currently using lenses or contact lenses? What are their future needs? How do they perceive this lens? And where do they do the purchase? Bo just showed a little bit about it. So 76% of the 600 people that we asked are very interesting. Only 8% find it not interesting. We have had, because I have, with all my experience in the industry, of course I know what we expect from the wearers, where the benefit is, and where they will, what the price points are, but we need to have it documented. And now we have the documentation that our glasses will be more comfortable, lighter, and all the problems that you have if you have a heavy lens today. For the business aspect, it's very interesting that the 80% would like to have the lens, and 50% of them would like to pay more for that lens than they are paying today. So between 40 and 50% are willing to pay 20% more. And if you have a marketing background, you can actually get a higher increase in that price if you start communicating about the benefits. So we're looking into a very, very interesting market for investors also. That was my 5 to 7 minutes. So if you have some questions about the market. Yeah.
So have you built prototypes ranging from like -1 to -10, and do they actually work?
Yes, we have built a technical setup of a prototype, and we are, within a near future, we are going to make a pair of spectacles. Yes, to see and test them towards the conventional products.
change your glasses?
I have my correction is not in that area. So and actually, what we are doing in the first part is to build the lenses only for one distance. I have multifocal, so progressive lenses. So I have far vision and near vision built in my lenses. That will be in a later stage. So we only go for the one vision, single vision lenses. So we will also target, by that we will target a more younger audience, because when you turn 45, then you start to having issues in reading. And then you need lenses for the long distance and for reading in one pair of spectacles. That will be in our later stage. There's a more complexity building these lenses, but not as we are not going to do it. We will do it for sure. Yeah.
How about astigmatism?
We have that. Astigmatism, we have that already. So that's no problem. Yeah. Are there any volunteers here? Who would try it?
I would like to try it.
Yeah.
Or I have my kids.
Yeah. Yeah.
Was born with a defect. So he removed this old step and is now using very thick
Yeah.
glass.
Yes.
And for the moment, he has a lens
Mhm.
and a contact lens.
Yeah.
So both of them.
Yes.
And when we look, when he, when he's not using both the contact lens and the lens, he has a normal lens, you can say, without
Yes.
lens. And then it's very thick. And when we look at him, he has those big eyes.
Yeah.
When you look into it.
Yes.
And what about, that was one question.
Yeah.
How will that look from outside?
Mhm.
Will your solution,
It will be less.
it will be less?
It will be less. Yes. The lens will.
Because I think that's also one,
Yeah.
in order not to, drille,
Yeah. 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 Yeah.
For the kids. So I think that there could be a market for
Mhm.
kids like.
Yeah. So the inner lens in the eye is around plus 12 and 13 diopters, and that lens we can make as flat as my lens, and it will not have the same way of disrupting the natural side of the eye. So it will not be magnifier. The lens will be a magnifier, but not in the same way.
I think that could be
Yeah.
a good market.
Yes.
In fact, I don't
Yes.
know how many, but I think that
No, but there are some.
with this kit, I could
Yeah.
think that it could be very interesting to have a test.
Yes.
Because you'll probably have an operation when he is 18 or
Yeah.
19
Yeah.
and so on. But in the meantime, he has to use glasses.
Yeah. Yeah.
So I'm a volunteer.
Fantastic. Yeah.
Stay in touch.
Any more questions? No.
Maybe one.
Yeah.
So your funding journey now, do you have any plans? Do you have anything lined up? Because you're like trying to raise a significant amount for the Danish content. So do you have your own money with you, or are you already in talk with investors?
No, we are, let's say, looking at the market, and of course we have some of our own money, but we need also an investor who can bring us to the next level. So it's not just money for now; it's also money for the future that we need. So the risk is that you get stuck, let's say, in 2 years, and you run out of money, and you still need some money to make the last part that could bring you bring the success. And therefore we need to build a solid plan for the next 3 to 5 years to see how much money we actually are going to need, and then we will have the right investor. And we'd rather have one big investor than many small investors. Yeah. But that will be the next journey that we will come to. Yeah. Thank you. So, Anders, I think you're the next. Yeah.
So, hello. So I think I know most of you here present in the room. So my name is Anders Christensen, and I'm a physicist, and I'm a professor here at DTU at the Department of Health Technology, and I've worked at DTU since 2001. In the next 10-15 minutes, I'm going to give you a brief tour into our journey from research to the innovation. And the title of my presentation here is Laser Printing Optical Metasurfaces. So, optical metasurfaces relates back to the discovery of Isaac Newton reported in the 17th century, that light is a carrier of information, and this information is coded into the light by interaction with materials. And then within the last few decades, thanks to the semiconductor industry, we have got tools to sculpture materials at the nanoscale, so that we can make engineered materials comprising nanoscale features or nanoscale parts, so-called meta-atoms, so artificial atoms, you could call them, which locally control the properties of light, namely the frequency, phase, amplitude, and polarization of the light. So this means when light interacts with such a surface as illustrated here to the right, that is reflected on the surface, then this surface is engineered with these small nano Lego parts there, so that it selectively absorbs, in this case, the red part of the light, so the reflected light appears to be blue. And this is also illustrated in the picture to the bottom, where you have such a surface, and then you have such nanostructures with different sizes of these small bumps. So in the central part, you can see a blue circle, or sorry, a blue square, and then in the bottom right, you can see the logo of DTU, which is red. And this is this surface of plastic, which has been covered with a very thin film, in this case of aluminum. So you can see that in the parts, in the parts in the periphery, where it's aluminum on a flat surface, so that's a mirror like we can use when we shave, and then when the same thin layer of aluminum is deposited onto our engineered nanosurfaces, then the surface becomes blue, or appears blue, or appears red, or whatever color in this case we want. So these kind of so-called structural colors or ink-free colors, they rely on that the material it absorbs the light at the wave at the light that at this optical resonance, and we made some research and discovered that you can actually also exploit this absorption resonance in these nano meta-atoms by taking a laser which also has the same wavelength in resonance with these meta-atoms. So in this case, we took a green laser, and the green light is absorbed by this apparently blue surface. And then it turns out that the green laser light is absorbed very, very efficiently. So we have a very efficient, energy efficient transfer of energy from the light, so to locally melt the material and ablate the material, heat it up. And this is illustrated in the movie to the right, where we are with you can see the laser spot, and then we are scanning with this metasurface underneath, and you can see that by changing, or modulating the power of the laser as we scan, then we can print different colors. So this is our laser printing of those metasurfaces. So we take something which is homogeneous, this homogeneous blue surface, which we can make in large quantities and cheap because they're identical. So we can just print them and then we can give it a functionality. In this case, it's a color image by using this so-called resonant laser printing. You can also say that what we're doing is that we are creating a laser printer system where we are laser printing on a special type of paper, just like these thermal printers that you use in the supermarket when you get your receipt from the cashier. That there's no ink in that printer. Sort of the ink is sort of built into the paper. Here, our paper is then this nanotextured isotropic surface. And then how can it be that we create different colors? Well, the colors, in this case, they appear because of different size and shape of these small nanostructures. So whenever we heat it up, and we can heat it up, sequentially or in different ways, simply just by selecting the power of the laser. So the laser, so each area gets a single shot of this pulsed laser. So it's illuminated for a nanosecond, and then depending on how much energy we deliver in this pulse, then we change locally those nanostructures from the original disk to something else, and that can be, you can see as we go down, we gradually increase the energy or the power of this the energy in this laser pulse. So we can start by just using melting or reflowing, so you're making the corner soft. You can de-wet the surface, so you get a small ball of the material sitting on top. And you can even sort of ablate, so remove all the material and start machining also underneath. And this gives different colors. So that was how we first demonstrated that you could laser print in colors on these metasurfaces. What I've shown you there in our first demonstrations, that was with metal, but then we also showed that you can also just as well do it with an isolator and a dielectric, and also this slide also shows how we can achieve a very, very large or high printing resolution. So as you can imagine from this slide, I can print your color photo on this within a single pixel on the screen of your smartphone. That's so I have this flexibility of making ink-free colors, and I have this extremely high resolution printer. Then I of course try to apply for a lot of money to commercialize this. As hey, we can do this. This must be of some use. But it turned out that you were trying to replace something that is cheap and works well. So that was very, very difficult. So instead, and then we had a lot of arguments for that we could really do a lot for the environment and what have you. But nevertheless, we never really succeeded in getting that way. So we started looking instead into making optical components. So we are thinking about can we make an optical optical components like like a lens or diffraction grating. And we would like, instead of having something that would be a reflection mirror with some color, then we would like to make something that would be transparent and do something to the light, like, for example, a lens would do. And one way of making lenses with metasurface, that would be to create so-called Fresnel zone plates. So it's basically a set of rings where we locally, again, use the same phenomena that the nanostructures that are placed locally, they can code, in this case, only the phase of the light, and so that we actually can get a focusing effect from this. And this is a lens which is then only of the order of 100 nanometers thick. So it's actually in the same. I mean, the thickness is the same as the wavelength of the light. So you may have seen such Fresnel lenses if you go to a light tower, and then you can see that they're carved out in glass. So you have these sawtooth. That has some disadvantages. This here is completely flat. This surface here, and has the same optical function. It does, when the light exits this structure here, you have done the same thing. You've coded the same information into the light as the big bulky glass thing in the light tower has done. But then, of course, when you want to have a transparent device, then the materials that you use to build it, they must also be transparent. And then we chose to, instead of using metals, or in the previous examples we used semiconductors, silicon and germanium, then we moved on and worked with titanium dioxide, because titanium dioxide is transparent across the visible range, which is what we want for our lenses, and then it starts absorbing when you go into the UV range. So now we laser write with a UV laser, which where in the range at wavelengths where the titanium dioxide absorbs the light, and then we use the device in the visible range where the material is transparent. So we have separated sort of the wavelength that we use to produce it, and and the wavelength where we range, or the color that we utilized the device. And this is an example of such a lens. So there's a question about high diopters. If you transfer and translate the diopter of this lens here, it's few hundred nanometers thick, and it has a diopter of 15. And it has and we have tried to illustrate the focusing effect of this lens here. And I think Sheng Li, who's working on Odyssey, she has actually brought some samples from the lab. If you experience by the fingers, then there's a chance afterwards in the networking session. So Sheng Li is sitting here. So that was my short tour on how we moved from something we were very proud to publish in a prestigious journal to forming a startup company and trying to make a disruption in an established business. And I would like to also thank sort of people at DTU who have been I've been collaborating on this, and also thanks to also Niels Asger Mortensen. He moved to University of Southern Denmark, and also Uri Levi at Hebrew University we work with. And then there's a number of research papers, and finally you can see also some of the different projects that has been we have generated these research results leading to the start of Odyssey at the end. So this I'll say thank you for your attention. Yeah?
Would it be possible to use this technology for the contact lenses also? Or are there any advances to the
In principle, you could use the same technique for contact lenses, but we have, I mean, it's actually part of our innovation journey that when Bo and I started working together, then we were actually looking at can we make diffraction gratings, can we make sort of other kind of more technical optical elements, and then and then Henrik got into the business, and so it was more like what is driving us here is really like spectacles or like is really the big apple. But maybe Henrik, you can say a little about why we sort of say we'll leave the contact lenses to other people.
Yes, it's interesting in contact lenses as well, and you can also in cameras. It could also be, but the market it's all niche markets. So the biggest market is actually the lens market, and Anders explained it very in a nice way that he have seen so many students developing things, trying to bring it to the market, but it never succeeded really. So what could be nice is actually that something that is come out of DTU actually reached the market, and this is why we are taking it in this step. So maybe in the future, yes, it could be part of a normal contact lens industry to have using this technology for contact lenses. Yes, there are many. Probably many industries where it actually could benefit, but our purpose is actually to entering into the lens market, to actually bring it into the market. Yes. Yeah.
Otherwise, if there are no more questions, yeah, there was a question there, Theodor. Yeah.
Robustness. I mean, the glasses, yeah, fine, but you get these glasses and you rub them with a cloth and put the fingers on them.
Yes, Theodor was actually also partner in the project Plast for Future, and he started many. He was actually on the journey with the colors, and there we had the same problem with abrasion, and you apply a protective coating on top. So this is a layer.
Is that also the case here?
This is you could say one of them, but actually you could say this film, thin film that we have on the top is actually a protective coating in itself.
It's a very good question.
Yep.
And it shows that you have some insight, because what we want to avoid is the smudge on the lens. So we want to build an anti-smudge surface that is in the conventional coatings that are on the market now. So all the coatings that are on the market now, anti-static and all these type of coatings, that we want to implement, of course, in our coating. So we have not been looking into that yet, but that will be not a big issue to put that on. We know exactly where to get the right people to do the right job. First, we want the optical technology to work, and then we have this as an add-on. It's just included in the coating. So, yeah.
Yeah. Arno?
The color kit is based on resonances, right?
Yes.
And I'm just thinking you need white light.
Yes.
So not really resonances.
Exactly. Yeah. But it's not a. You're absolutely right, and this is also part of this design. Also, that we I think before when we talked with, we had a representative from Innovationsfonden who funded us in 2018, and Mikael here from Skylab was teasing me, saying, okay, that's 5 years ago, and I'll say, well, we have been changing technology every time we, or sort of with the different projects. So it's not a Mie resonance type metasurface that we have here. But you're absolutely right. This is I mean, chromatic aberrations is also something that is part of what you have to engineer here. Yeah. Yeah.
That's a whole ball game. The name Odyssey.
Yeah.
What is that?
That's the name of the European. That's the acronym for the European project that we're disseminating today. So it stands for On Demand Eyeglass Lenses Laser Printed in the Shop While You Wait. So the U is while you wait. Yeah. Yeah.
I thought there was something.
Yeah. This is and I think and we're really proud of having that. It's that acronym.
Yes, really impressive. And While You Wait is actually because our idea is actually to have, if you have been in the optical shop, you see all the frames, they are hanging in the shop. All the frames have a thin lens. That is just a demo lens. It has no function at all. So our idea is actually in the long term is that it's our lenses that are the demo lens. And that lens that are in this frame is actually already prepared with our nanostructure. That means that the end consumer enters the shop, choose a frame, the refraction is done by the optician, and then while they wait, have a cup of coffee or whatever they do, we put the frame with the lenses in a laser, and the job is done. Then they have the ready spectacles. That is our end goal, to bring it to that stage.
And today when you buy glasses, I don't wear glasses, how long time does it take?
2 weeks at least.
Okay.
At least. Yeah. So the process today is that you get a refraction, you choose a frame. You are limited with the frame because depending on the prescription that you have, if you are wearing thick lenses or whatever, high astigmatism, then the optician has to be careful to choose the right set of frame, because afterwards you will have discomfort or it will be not very handcrafted, well done. So that is where you need experience from the staff to choose the right frame for you. So you have limitations, and in our system you will have no limitations. You can choose whatever frame you would like to have, because the lens is thin, and we can make it immediately. So you can get your glasses immediately. Like when you go to the car dealership and you want to build your car in that color, also there you have to wait. But if you could imagine that you could just get the key immediately and you could drive away. This is what we are going to do. Yeah, and that will be a disruption, for sure.
Okay, so if there are no more questions, then we should move on to the last presentation.
See if we can get the technology to work.
So I can just unplug here, right? Yeah.
My name is Nikos Kechayas. I'm CTO of the company Nanotipos, which is based in Greece, and I'm very happy to be part also of this EU project Odyssey. So I will give you the perspective of how we are fabricating these optical metasurfaces, these polymer optical metasurfaces, and we'll just touch base on various parts of the manufacturing value chain. I cannot disclose most of the things in terms of material, dimensions, and so on, but we are open for any kind of discussions afterwards. So who we are, very quickly, who we are a pioneering R&D company, which is mission is to create, develop, and commercialize products which are realized by nano patterning or nano imprint manufacturing technique. We were founded in 2012. We have more than 18 years experience in nano imprint lithography. I heard Theodor Nielsen is there. So I started my PhD together with Theodor, so I'm very happy that he's there, and he's become very, very successful in this field. So as I said, we mostly do R&D projects, both with public authorities or with companies. The main motto behind our technology, I'm sure you're aware of it, and what is being presented today is that by creating micro or nano topographies on surfaces, we can create added value products and intelligent functionality. So that is the key aspect of our technology. And what we are working on is to try to develop processes and technology and leave from the demo cases or from the lab scale and try to move things towards higher TRL levels. Now, no matter what size of the dimensions of the structures we are imprinting, we always are interested and we are working on finding the suitable nano-replication technologies to do this upscaling. So in-house, we do have a lot of replication or nano-patterning tools, starting from the CNI tool from Nil Technology. We have 3D printing. We have a small micro-injection molding tool, thermoforming. Recently, we purchased the 350 millimeter wide web blow film extrusion equipment, and of course some nickel electroplate coating technologies. Our role in Odyssey is the objective is to fabricate these templates. I mean the master stamp, and also to replicate them in a working metal surface foil. And the way we envision to do this is by nano-imprint lithography-based methods. So I will not stand much on nano-imprint lithography. So the basic idea is that we have a thin film, a thin polymer. It could be a thermoplastic or UV curable. We put it in contact with a stamp, with our mold, and once we either cure or heat to allow the polymer to flow in the stamp cavities, we can easily, let's say, replicate the negative features of the stamp. The evolution of batch-to-batch nano-imprint lithography is the roll-to-roll. So in this case, instead of having a hard substrate, a silicon or glass substrate, one can use a flexible mold, which is covered over a drum, and in a continuous way replicate the micro nano topographies which are on the stamp on a flexible substrate, again either by temperature or by UV light. So the main challenge of Odyssey project was, first of all, to fabricate a silicon stamp which had the high demand in terms of critical dimensions. So the structures we were attempting, or which we fabricated, were had a very critical point in their specifications in getting right all the dimensions. And the main question at the beginning is with what polarity we have to start working. Will it be pillars we have to fabricate in the silicon master, or will it be holes? Then the next step is the master replication. So we had fabricated a silicon stamp, but because that costs a lot of money, we don't want to break it, so we have to secure it. So we had to generate a working stamp, a so-called working stamp, in a special material which will keep the critical dimensions of the structures and use that as our mold to replicate that into our actual lens. So that comes to the point of what is the replication technology that we have to use, which is suitable not only for the prototype, but also for the mass manufacturing of these optical lenses. And our thought from the very beginning was to use something that the industry is currently using. So we did not want to change much into the industrial process of what our colleagues in Optilex is using to produce these polymer lenses. So we had to use something very close to their technology and use, if possible, the same materials. So that was our starting point. As I said, we started working or trying to find out which polarity had to be fabricated. We started with pillars, and then eventually we saw that that is not the right polarity. So our final process came up of creating silicon molds which had holes. And not only by creating the critical dimensions in terms of the diameter, but we had the requirement that was also to have high aspect ratio structures to get as high as possible, high aspect ratio silicon hole structures, and maintaining the critical dimensions. And that was not an easy task for us. It was very difficult, even maintaining the tilt angle of these structures. We struggled a lot to achieve our final results. Going into the working stamp, the first material we thought that could potentially replicate these kind of features and from holes achieve pillar structures was PDMS, but that was not really the case. PDMS is a nice material that could be used for micro replication or sub-micro replication, but in our case, because we had high aspect ratio structures, very small in diameter size, we were not getting a very good replication fidelity by using a PDM stamp. So that's when we started seeing what is in the market in terms of material which could be used as a flexible mold. And we were not really happy with what was in the market. So we went and we started developing our own fluorinated polymer, UV curable polymer material, which is the case. And we were very successful in getting very, very nice results of replicating our Silicon Master stamp. So the other thing is that, okay, we had our material. How do we replicate? Is it very straightforward to replicate so high aspect ratio structures? And the first experiments, we saw that it was not an easy task. So we got phenomena like the collapsing of the pillars and them attaching and making all these aggregations. So working out slowly and developing the printing parameters, chemical parameters of the material also from the material which the stamp is made of, and also the embossed material, which is also a key point. We did finally achieve to get a large area. Large area means 3 by 3 square centimeter areas of a working stamp. This is a UV curable resist material which has been deposited on a PET substrate. So in terms of replication, as I said, we wanted to follow the approach of industry. So the easy way the less complicated, let's say, approach that industry is using to make these lenses is to use a mold, a universal mold, which we place below a quartz substrate. We attach to this quartz substrate a thin our working mold. You attach on top, you close the mold with another quartz capping layer or substrate, and then within the gap, which is within the ring here, we insert the UV material from which the lenses are made of. So we follow the same technique. This is just a cross section of having 2 glass molds, our patterned film, our working mold, inside which has a spacing, so we can control really the thickness and correct and replicate by this simple molding technique the nano features on our UV curable resist. So this is just some images of the process. how it was filled, the rubber ring, and how we are filling in the UV material. Now, this UV material is the one that industry is really using to produce lenses. So we kept same process and the same material. It was fun enough to see that this material was suitable also to replicate these nanoscale features. But one problem that we face is that, okay, we replicate these nano holes in the suitable material, but then we have to cut it into and form it into the actual lenses. So because we did not have the appropriate size of working stamp, it was kind of difficult also from the processing time and speed to also go laser cut this into our actual lenses. So we thought, okay, why don't we just replicate the same process, and instead of having a universal 4-inch, let's say, area where we are wasting a lot of material, why don't we just go cast directly on our pre-designed lens? So we took the actual 2D designs of the lens, of the actual lens that the end client would like. We 3D printed a mold, which we replicated, a hard mold, which we replicated in PDMS, attached that PDMS mold to a silicon wafer. So we created our own universal mold. We pour in our UV monomer. This is the monomer that we developed. And then by placing the polymer stamp on top and exposing to UV light, we can really structure the complete lens, targeted lens product. So this is just some images of the actual lenses. So these are about 4 centimeter wide lenses, fully patterned, very nicely. The transparency is there, planarity is there. We're still continuously working, and within this time frame of the projects, we did develop our own materials, which are suitable not only to replicate, but also to meet the standards of the post-processing processes that are required to really fabricate these meta surfaces. And by post-processes, I mean some coating, etching, and developing processes. So this material is resistant to some chemicals, heat, and funny enough, these are flexible, so they don't break. So that is a good thing if also discussing about safety issues or meeting the safety issues or the requirements, that are needed when we apply these lenses as working lenses on the frames. So what I presented up to now was like really flat lenses, which was the goal, but it might come out that we require at some point to put these nanostructures on curved or to fabricate curved lenses. So we do have developed the technology to solve this problem. So we are able to very nicely uniformly create nanostructures, like also microstructures on curved lenses. So this is something that we are constantly developing and working on to meet the needs and the specifications that will come out in the future. So some acknowledgements of my team. Stratis, he's a chemical engineer who developed all the materials. Kostadina, who's the nail expert. Thodoris, who is the roll-to-roll nail expert. So at some point we did replicate our working molds so we can lower down the cost, the manufacturing cost, by roll-to-roll nanoprint. So we have really thought about the next step of industrialization. And of course, I have to thank you, Nil Technology, for providing us the CNI tool, which without that tool, I don't think it will have been possible to achieve all these results. So thank you very much. I'm open to any questions.
I'd just like to round this off and say thank you everyone for turning up. It's been a pleasure. It's also been very nice to receive all your questions. It's always nice to test your case in a real audience and people who have been from the outside and say, okay, what do people think when they hear about this? And is there anything we haven't thought about? There's always things coming up and say, okay, I didn't get that exact angle. So that's been very nice. If you're interested in some of these presentations, you can just contact me or Skylab, and we're willing to share them, because we, of course, didn't reveal any confidential information in this event like this. So, and yes, once again, thank you everyone for showing up and making this a great day.